Welcome to Wednesday NASNI Talk.
Good evening, everyone, and a very warm welcome to 40th online NASNI Talk. It is my privilege to welcome you all on behalf of the National Astronomy Network of IAPT NASNI. We are honored to have with us today the National President of IAPT, Indian Association of Physics Teachers, Dr. P.K. Ahluwalia. I am also delighted to welcome the founder members of NASNI, Dr. Arvind Kulkarni, Dr. Ranjita Deka, and Dr. Reshma Desai. We are equally pleased to have among us our participants, including our previous NASNI speakers, Madam Amoli Kakkad and Dr. Foram Joshi. A warm welcome to all of you. Today we are privileged to have Dr. Brijmohan Thakur as our guest speaker. Dr. Brijmohan, it is a pleasure to welcome you to this NASNI talk. Now, without further ado, I would now like to invite Dr. Foram Joshi to introduce our guest speaker and formally invite him to deliver his talk. Dr. Foram, over to you, madam. Thank you.
Good evening, everyone. It is my great pleasure and privilege to welcome you all to today's online talk. We are delighted to have with us Professor Dr. Brijmohan Thakore, a distinguished physicist, teacher, researcher, and science communicator. Professor Thakore is a professor in the Department of Physics at Sardar Patel University, Anand, Gujarat. He holds an MSc in Physics and MPhil in Experimental Solid-State Physics and a PhD in Theoretical Condensed Matter Physics. He brings with him an impressive 34 years of teaching and academic experience, including 23 years in the postgraduate department of Sardar Patel University. His academic and research interests span several fascinating areas, including astronomy, computational physics, and condensed matter theory. His research work has resulted in 63 research papers published in international journals, and he has successfully guided 6 PhD and 13 MPhil students. He has also undertaken a UGC major research project on technological materials using pseudo-potential theory. Professor Thakore has also made significant contributions to science outreach and popularization. He served as the honorary director of the C.C. Patel Community Science Center, Sardar Patel University, from 2016 to 2019. His academic journey has also taken him internationally, including an academic visit to the prestigious Abdus Salam International Center for Theoretical Physics, ICTP, Italy. He is a fellow of the Gujarat Science Academy and a life member of several professional scientific organizations, including the Indian Association of Physics Teachers, IAPT, Materials Research Society of India, Indian Physics Association, and Bird Conservation Society of Gujarat. With his rich experience in physics, astronomy, research, teaching, and science outreach, we are truly fortunate to have him with us today. On behalf of NASNI and all the participants, I extend a very warm welcome to Professor Dr. Brijmohan Thakore. Sir, we are looking forward to learning from your knowledge and experience. Over to you, sir.
The rotation period of the sun based on the rotation of sunspots, etc. All will not be possible. I will try to focus on a few things. But before we do all that, we must know the our camera. Our camera, DSLR specifically, many people now have DSLRs with them, and they try to photograph the phases of moon or maybe deep sky. They do some stacking, and this simple image schematically tells us about the optic train. Here, this lens represents the telescope optics, more than one lens. combination of mirrors also for a different design. And on here at the back side is shown a camera chip. The digital camera chip, which is there in all the cameras, is just a matrix of pixels. So there will be some number of pixels width-wise and same way height. And when we photograph celestial objects, the image is formed on the sensor. Now this camera chip, the specification of the cameras are given in the manual, and we have lots of cameras available in the market, from full frame to small cameras embedded in our mobiles. The numbers which I will share with you will be for the DSLR which I have, and that is a Canon 700D. It's a APS-C sensor, and the dimensions are given here, 22.2 by 14.8 mm. If you have a different camera, the size will be different, the pixel size will be different, but that thing will help us to extract scientific data from our photographs. Of course, our camera chip, the pixels are having a Bayer matrix where you have 2 green, 1 blue, and 1 red covering a given pixel, so that we can do some color photography. Okay, and if I talk about the camera which I use for my astrophotography purposes, combined with my telescope, it's a 700D, and it's 18 megapixel. An 18 megapixel simply is nothing but the multiplication of the number of pixels along the width and the number of pixels along the height. So you have 5184 pixels into 3456 pixels, which turns out to be 18 megapixel. And the size of the pixel, I cannot see it here because I've written it, I think, but the sharing message is in front, fine. So its pixel size is 4.29 micrometer. And that these 3 numbers are very important. We can do size calculations. Let us first try to understand how much field of view is covered, how much amount of sky is covered by our camera. In this case, the field, this is the focal length, and this is our sensor, and this forms a right angle triangle. So the object is focused here, it forms a right angle triangle, and a simple formula will be tan inverse W upon 2F. Okay, so field of view width wise and field of view height wise we can find out. And in this case, for the kit lens at 18 millimeter, I will be able to cover 63 degrees by 45 degrees of sky. That's a huge amount. Entire constellations, entire chunks of sky will be covered on the sensor, and this will be helpful if you are trying to film the Milky Way. But other objects naturally are at 18 mm. This is the amount of sky which my sensor covers. If I use the camera at 55 mm, then this reduces to 23 degrees by 15 degree. And the comparison tells you that at 18 mm, this is the size of the moon. At 55 mm, it's good enough to will be covered. And this is a simple comparison of my camera alone working at 250 mm. And this is good enough to, measure the dimension of the moon pixel wise. And of course, we have to convert it into a different unit. If I use the same camera using a T2 adapter and connect it with my Celestron 8 SE, it is having a native focal length of 2032 mm. And then I have such a good view that I can, Mare Crisium here, Plateau. We can study individual craters also. Before doing any calculations, we'll first have to find out the camera image scale, and that is correct for any given camera, right? So we have to find out how many arc seconds of sky is covered by 1 pixel. And for that, this simple formula is there. In 1 radian, this is the number of arc seconds. So this will be this number multiplied by pixel size. This you can find for your camera in the manual. Specifications are given and pixel size is invariably given in your manual. And you of course know the focal length at which you are photographing the sky, night sky. These two have to be in the same units. And so at 18 mm, this is the amount of sky which is covered, and this is arc second per pixel. So if I am using my camera at 18 mm, then each pixel will cover 49 arc seconds. As I increase the focal length and the field of view becomes smaller, at 55 mm, the pixel covers 16 arc seconds, and at 250, this is the number. So once you know these numbers, it is easy for us to find out size, etc. From our photographs. This will help us. So this is the lunar eclipse, which I had photographed at 255 mm, and this is the size of my sensor. So it is 5184 pixels width wise, and height wise is 3456 pixels. Once I know this camera image scale for the wavelength which I am using, say this is 3.5, then it will be easy for us. A simple calculation, see the images of a lunar eclipse, and we can measure the diameter at this point also. Okay, one simplest thing which can be done is kind of zeroth order. You can whatever you have photographed, you simply put in the printer and take out a printout. This is the A4 size page, and the dimension of the printout, the picture is 270 mm, which corresponds to the width of the camera sensor, and here it is 200 mm. So 200 mm corresponds to this. And for school-going children, you can simply measure the dimension of this using a scale which you have in your compass box. This comes around 6 mm. Of course, lots of error will be there, but 6 mm. And that 6 mm corresponds to 115.2 pixel, right? And then we use this arc second plus pixel. This is 16 arc second per pixel at 55 mm, because this has been photographed using a 55 mm focal length. And then we can find the angular size by simply multiplying the number of pixels here and multiplied by this arc second per pixel. So that gives us roughly 0.5 degrees, and that's fine. But if you are trying to extract scientific data, we should not use this simple method. What can be done? We can use a CAD software or something, and not simply measuring the dimension like this. This point represents of my camera, and as far as this image of the then we can find three sides, and then using this expression we can find out the diameter. So with these numbers which I have shown, if I plug in those numbers, but we must remember that these are pixels. This is pixel number, this is pixel number, and so whatever diameter we get will be in terms of pixels, and then we have to multiply it with the arc second per pixel. So it depends on the focal length. You have to pre-calculate for your focal length, your camera sensor, what will be arc second per pixels. So I have this coordinates of these 3 points, and these are the results. I will not show all the numbers for other the projects, but for this I am showing. So this D which we get is around this many arc second. So that is roughly slightly greater than 0.5 arcsecond, and that is correct for the moon. So this is how we can find, once you have photographed the moon, transfer it into a computer PC, use a CAD software, open the image, select 3 points and make a circle, and then we can do the calculations and find out the size of the moon. Next, I will try to show how we can measure the phase of the moon. The phase is defined by this. If this is the day part of the moon and this is the terminator, this the night part, and you have photographed this, you simply measure this to the total diameter of this, and the ratio illuminated part and the diameter of the moon will simply give you the phase. So let me try to show you. I will go outside the PPT and try to show. Suppose I have is visible. This CAD program is visible.
Yes, sir.
Yes, sir.
Okay, fine. So we can just import and insert an image, and suppose I select, say, this image, fine, open, and then I put it here. This is the 0, 0. Okay, so you have this. Now if you go in tools, it will be different for different CAD. What I'm trying to show is how it can be done. So we can select a circle and 3 points here. So 3 points we know uniquely defines a circle. We can just put 1 point here, another point, let me put it here, and then the moment I put the third point, you can see the circle is okay. So this is how we complete the circle, and then if I just click it, it will show the center point also, and then you can use a measure. How to measure? There are various things given, point to point distance or one, whatever. So this way you can find out, or you can simply write down the pixels for this, and then it can be done. Okay, so let me skip this. I've showed you how it can be done, but you can first import the moon picture which you have taken, then you can complete the circle like this, and then in order to find out the phase, we have to find out the illuminated part, okay, into the total diameter. So I'm putting a terminator here. See, this is actually the terminator is an ellipse, fine, but for finding the phase we just need the last point here on the terminator along the diameter. So you can do that, and once you do that, then measure. This is say 3126, and the total diameter is, this is number of pixels, 4586 pixels. So once you do that, you can simply take the ratio and you have the phase, that is 0.68. So in this way we can find the size, and not only size, we can find the phase of moon also. Another thing which can be done, because see, once we know how to find the size of the moon, that can be applied to find the eccentricity of the moon's orbit. This is a schematic diagram showing you the orbit of the moon, and we know that because it's an elliptical orbit and Earth is at one of the foci, moon while moving in its orbit will be sometimes the nearest, and that point is known as the perigee, and when it is farthest it is known as apogee. Now because this distance is large, it will appear smaller, and when the moon is nearer in its orbit to the Earth, it will appear bigger. So the size of the moon changes as it moves in its orbit around the Earth. And because we know how to find the size of moon, that can be very well applied to find the eccentricity of the moon. This simply gives you the comparative picture of how the moon appears in the sky. This is regular. This is when the moon is at the perigee, so what we call supermoon, slightly larger in size. And when it is away, it will be slightly smaller. Now, if you know how to find the size of this and this, it is very easy to find out the eccentricity of the orbit. It will be perigee and apogee size this. Okay. Now, what can be done? The difference is around 14% in size. Right? And we know that the angular size of a celestial object like the sun or the moon will be naturally proportional to, inversely proportional to the distance. The farther it is, the smaller it will appear. So when the moon is nearer, the expression for the distance in terms of eccentricity E and semi-major axis of the ellipse will be given by this. And when it is farther away, the apogee, it will be like this. So if the ratio is taken, it will be like this. Okay? And if you solve this expression for the eccentricity E, then because constant factors which come in, proportionality constants will cancel out, and the E will be can be computed using this expression. It is simply the angular size difference of angular size when it is farthest and nearest, and divided by it would angular size at apogee and perigee, the addition. Yeah, so it can be understood like this. Say this is an elliptical orbit of the moon. This is the semi-major axis A. Earth, let us now suppose that Earth is at F1, and from the center the distance is C. So the closest distance will be when the moon is at point B, that is BF1. Okay, and that will be simply given by, if you look at the figure, from center to F1 it is C and semi-major axis is A. So it would be A minus C. Okay, and when the moon is on the other side, apogee, farthest, then the distance from A to F1, that would be this semi-major axis A plus this C. So it would be in terms of the semi-major axis distance, it would be A minus C at perigee and A plus C when it is farthest. So we know eccentricity of an elliptical orbit is given by C by A. I multiply by 2 and divide by 2, so it remains same. This 2C I can write as C plus C, and this 2A I can write as A plus A. Now I do one thing. I add and subtract A here, and on this side I add and subtract C, and then rearrange these terms. So this will become A plus C minus this A minus C. And same way I can write it here as A plus C plus A minus C. Okay. So then C upon A will be A plus C minus A minus C. That's the difference, like perigee and apogee. This is perigee distance, this is apogee distance. So this will be a subtraction, difference of these two, and here it will be addition of these two. A minus C gives you the angular diameter at perigee, and A plus C will give you that at apogee. So if I just plug in some numbers which I have measured for my set of photographs and substitute, this is A plus is nothing but the angular size of the moon where you have photographed. Okay, and same way this, because it is further away, the number is smaller. When it is nearer, the number is larger. So the difference of these two, and here the addition of these two. Once you plug this in, you get C by A, the eccentricity of the moon's orbit. So that is this much, 0.055, fine enough. So three major steps are there. To imagine
image the moon at perigee, okay, and apogee, find the angular sizes as described in the first part, and find the differential ratio. So this should give you the eccentricity of the moon's orbit. So if we have a camera whose pixel size, focal length, all we know, and we photograph the moon at particular instance when it is at perigee, apogee, or for finding the phase at any given moment, for finding size also at any given moment, just taking the photograph of moon at proper instances will help us to find not only the size of moon but the phase of the moon and also the eccentricity of the orbit. Okay. Now this is not, let me tell about some periodicity, because I am talking about full moon at perigee is, what we call supermoon. This is not about photograph, but understanding how you can predict when another supermoon will come. So I have drawn this figure, which is not to scale. The Earth is slightly away from the center, and the moon is say here. This point is when the perigee we have a full moon, 19 February 2019. So because the full moon is at perigee very near, it will be a supermoon. And the question which comes to our mind is, when will be the next supermoon? So for that we can simply do some calculation, small calculation. We know perigee is 27.55 days, which we call anomalistic month, and full moon to full moon is our synodic month, okay, and that is 29.53 days. So both of these, when occurring at the same day, we have a super moon. The moon is at perigee also, and it is full also. What will happen after one perigee? One perigee is this 27.55 days. So I'm supposing this orbit remains just like this, and you again come here, the moon comes here. Still, one perigee to another perigee is 27.55 days, but full moon is 29.53 days. The next perigee, it will not be a full moon. Full moon will be 2 days past, okay, like this. Next full moon, again it will be 2 days past the perigee, and so on. It will, just assuming right now, just for explanation, the perigee is here. Okay. So, how do we find it? Two conditions must be satisfied for a super moon. It should be at perigee. So, this is anomalistic month, perigee to perigee, and this is this. All we have to do is simplify and solve this equation. 27.55x is equals to 29.53 something y. Okay, and in order to do that, we can take the ratio 29.50 full moon synodic month divided by anomalistic month. The ratio comes out to be 1.071713. We can write as a continued fractions like this. It will go on. Now what we do? We first keep one term. So it will be 1 plus 1 upon 13. So that could be 14, 13, and that is this number. Not exactly matching. Then we take yet another term. That is 15 by 14, and that is this term. Okay. And third, one more term, it is 269 by 251. Now this is exactly matching. But this many months, nobody will have the patience. So if you come here, 15 by 14, 15 multiplied by this many days is 413 days, and 14 full moons. So after 15 animalistic month or 14 full moons, you again have the same number of days. So if we have a super moon, then after 413 days, that is after 14th full moon, will again be near the perigee, and it will be a super moon. I hope everybody is there and listening to me. I cannot see anybody, and so it's like a corona time where I used to take lectures, could not see the students, nothing big, sitting in a room and lecturing.
We are available, sir.
If you know how to find the eccentricity of moon by taking two pictures when it is nearest and farthest, same thing can be done with the Earth's orbit. But the difference is that every month we have a perigee apogee distance, whereas the once in a year, around first week of January, 4th or 5th January, it will be nearest, and then in the first week of July, it will be farthest. So, if we take two pictures of the sun one in the first week of January and one in the first week of July, then we can see that the size of the sun is different. Of course, we have to take proper precaution for photographing the sun. Okay, and this I've done with my C star. The C star is useful in that sense. The focal length is fixed; it does not change. And this is the image scale. This many number of pixels multiplied by this many number of pixels. Pixel size is this. Of course, I had to take it on the first week of June, but it's monsoon time, so I took it 10-12 days before when the sky was clear. And when I put side by side, and I cropped it just touching the periphery of the sun. So here you can see that it is when in January the size of the sun is relatively bigger compared to June. Okay, and this we can put in the same set of equation. I'm not repeating. We can do and find the eccentricity. So for the sun also, if we take the picture, you can find the size, and we can also find the eccentricity of the Earth's orbit. This is just a caveat. Okay. The thing is, if you want to see the sun using a telescope, recommended is a full aperture filter. And if you want to do measurements, we must project. This is a projection using a 2.5-inch refractor, and here I have projected on the piece of paper studying the students. Or a mirror can be put and projected on the sun image can be projected on the wall. This is I've taken this image in 2005, projected on the wall. But the best thing which I'm using after 2016 is the sunspotter. This is the solar eclipse of June, summer solstice, 2020. And this mask reminds us of our torrid time we had, pandemic times, but it was lovely. And we can draw the circle to find the size also. This is the moon. We can find the size of the moon also by drawing a circle. And this was also fantastic for anyone who don't have any telescopes or something and no protective measures. You can stand under a tree and see thousands and thousands of eclipsed sun. I hope it is clear. So many eclipsed sun on the ground. Okay. Suppose you have a camera having a proper filter and you take a photograph of the solar eclipse. This is the sun and this is our moon. And this was taken on 26 December 2019 and written the perihelion aphelion dates so that here the moon will be nearer and the earth will be relatively far away, and so this will decide if we'll see a total or annular if it is on that path, otherwise it will be partial. But once you have this picture, again you can upload it in a CAD program, draw a circle here around the sun and select 3 points here on the moon and draw a circle here also. Then all you have to do is draw a line passing to the center of the sun, which is not visible here. Center of the moon also not visible. You have to find out using the CAD program as I showed you. And then we can simply find out the magnitude at that given time, because the magnitude of the eclipsed sun is simply the solar diameter, which is fraction of the solar diameter, which is covered by the moon. So if you see in this figure, this is the fraction of the diameter. This is the sun, and this is the fraction of the diameter of the sun, and this is the total. So if you simply take this ratio, then we can find the magnitude. Another thing is, if you have a CAD program or something, you can find the area also, which is covered. Because generally people think that if magnitude is 0.5, then the area of the sun which is covered will also be 50%, half. But it is not the case. If you see this figure, see this is how much 50% of the sun is covered by the moon. So this divided by the total diameter, that gives you 0.5. Magnitude is 0.5, but you can see that this area is 50%. So this area and this area is also visible. If the magnitude is 0.5, then the area which is obstructed will also be greater than 0.5. So one more calculation like this can be done to find the obscuration of the solar disk, area which is covered. And this is not a schematic diagram. This is a from scratch a scaled model diagram which I have drawn, which I had drawn.
नहीं लिखा है उन्होंने, बल्कि टिक करते रहे साथ साथ कि इन्होंने भी ले लिया.
Study how the solar eclipse will appear at our place. We can start from
आपने तो साथ के साथ दिए थे.
This is the descending node because this is the ecliptic. The moon is coming from above and going down, so this is the descending.
नहीं पता नहीं कैसे काम है इनके ना, क्या करते हैं.
Diameter of moon and diameter of sun ratio is 0.95, and we can find out magnitude is 0.6.
स्टेज है.
Everything can be found, and we can find out the first contact.
नहीं मेरे सामने दिया आपने लाके, मेरे को पता है.
One thing which
बल्कि मेरे से पहले दिया, मैं तो बाद में
2 units means this is just in centimeter or inches, and that has been equated to time
कमाल कर रहे हैं.
to degrees also, because we have to plot proper angular size of the moon and the sun.
नहीं तो बड़ा
At the same time, to find out the
embarrassing
time,
होता है ये तो.
we have put time on this axis, so we have to have 2 units parallel, one
नहीं
relating to time, another relating to degrees.
मेरे सामने
Solar
वो
rotation
टिक करवाता रहा उनको,
rate we
बल्कि
can find out.
मनोज
Tell me
को.
when my 50 minutes are over. Fine. Find solar rotation rate also from the photographs, because once we photograph the sun, there will be spots.
नहीं तो जो आपके पैसे हैं वो किसके नाम पे इन्होंने चढ़ा दिए,
One more time,
क्योंकि पैसे तो होंगे ना जेब में
4
उतने.
days later, then we'll find that the spots have moved. And from the amount which the sunspots move will help us to find the solar rotation rate. We know it rotates in 25 days around the equator, because it's a differential rotation, and it will be slightly, I think, greater than 30 days. It will be around 32 days in some cases.
और पता नहीं
So it's
इनकी
a
वर्किंग
differential
स्टाइल मुझे
rotation.
तो पता नहीं लगा
Rotation
ना.
is
और मैंने
identified by
वो
the
उद्देश्य वाला कागज जो डाल दिया
number.
उसके बारे में क्लेश करके बैठे हुए हैं कि ये क्यों डाला आपने.
See, if you don't have a camera,
ऑब्जेक्टिव्स
you
नहीं
can
हमारे
download
उसके
from
हैं.
the websites, Soho or Space Weather,
उसके
and do calculations.
नहीं मैं उसके
It's not
लिए इन्होंने
necessary
किया
that
हुआ, ये क्यों डाला कहते हैं आपने.
you can use somebody else's photograph or download images from the net and find out. As you can see here, this number,
अच्छा.
sunspot number 1861.
अच्छा जो सेक्रेटरी है वो अपना काम करता नहीं है, मनोज को दिया हुआ सारा
3
काम.
days time, 16 October, to this
और चौधर के लिए सेक्रेटरी नाम लिखाया हुआ है प्रीतम सिंह ने.
and this can be calculated using these images, or again
ये treasurer है
some
वैसे.
images I am showing which I have taken. This was sun photographed on 14th. The rotation is along this.
स्टेज को तो
Depends on the,
स्टेज को तो
I'm using the
उसका काम दिया था सिर्फ जो हमारे ये लगाने हैं ना.
and the time also of the
नहीं,
day
नहीं, नहीं.
when I photograph.
इस
Because,
पर्टिकुलर काम के लिए
parallelity
उसको
can be
असाइन
changed.
किया था कि ये काम आप
Whatever
करो.
is near the horizon
है ना.
in the morning when the sun is
वो
setting,
मतलब आगे फर्दर ड्यूटी दे दी ना उनको,
H will
और
be going
उनके
down
साथ थे.
So in 4 days time, this spot which
उनके
was
साथ
here
आप थे या कोई और था, मतलब 2 लोग लगाए ना हमने.
can be. So this schematically shows you
हाँ रोहित या
by
स्टेज
what
एंड
amount
रोहित, यस.
the sun
हाँ ठीक
spot
ठीक.
moves.
वो है.
There is a typographic error here. It should be T2, D1 when that is at time T1, and D2 at time T2, T.
नहीं मैंने तो मेरे सामने दिए हैं
For
आपने. कमाल.
accurate measurements, Stonehenge discs are used.
मेरे को याद है बल्कि बिल्कुल. हाँ
And
मैंने तो
E
बल्कि
value
सबसे
stage
बाद
is
में डाले अकाउंट में उनके.
7 to. So right now we are not using it. This is just a beginners amateurs project for.
आप अंदर से
finding the
लेके आए
solar
थे, मुझे
rotation
पता है.
rate. And the rotation rate
हाँ,
can simply
मुझे
be
पता है,
found
हाँ
out
जी.
by this sin inverse D2
हाँ,
by
हाँ,
R. Now why sin inverse?
नहीं
See, this is say
हाँ, हाँ,
D2
ठीक है.
or D1 divided by R. R is the radius of the sun. The sun is a three-dimensional object. We take the photograph on a 2D plane. Okay, so this can be, when you do that, you have to incorporate this sine inverse term. So that will be sine inverse d2 by r minus sine inverse d1 by r and the time difference. So if the time difference is say 2 days, it will be 2 days, 4 days, fine, 4 days. Okay, and that will come in degrees per day. But if you are photographing the sun after a gap of 8 days, this term has to be incorporated. Why? Because say you are photographing the sun on day 1 and the sun is overhead. Next day around the earth has moved by 0.986 degrees, because in 360 degree complete revolution around the sun is in 365.25 days, roughly 242 in fact. So that comes to 0.986 degrees per day. So that has to be incorporated. So if I'm using say these two figures to find out, there's a difference of 4 days, and therefore I will have to add here 4 multiplied by 0.986 degree. Once you plug in those numbers, you find the solar rotation rate, and it will depend on where it is. If it is near the equator, you should get around 27 days. But if the sunspot is at a higher latitude or a lower latitude towards the pole, you may get it in excess of or in near 30 days. How many minutes I have left?
We have 10 minutes,
10 minutes, sir.
10 minutes, fine. Another thing, let me show you. We can find, if you have a grating is used in all physics laboratories, undergraduate or laboratories and MSc laboratories. And if you have a camera and you put it up, of course, this is a specific star analyzer grating, which can be fixed here. In the lab, if you have a rectangular, no problem. But that is around 600 lines per mm, and this is 100 lines per mm. That's the difference. Once you put this grating here and mount your camera on a tripod and take a picture, this grating is a blazed gratings having such design. Put it in simple words, a blazed grating is a grating which gives you extra intense first order on one of the sides. We get zeroth order, we have first order on both the sides, but you are using a blazed grating like this. It will give you a extra bright first order, like you can see this in the star, and this is bright enough. Here you have not so bright spectra. This is first order spectra of this star and first order spectra of this star. Fine. So this is because many faint stars are there. We require a very large amount of exposure. So to avoid that, the design is a blazed design. And if you take a spectra which is like this, of course this is not parallel to this axis. So I can move this picture and crop it so that I have the zeroth order star here and the corresponding spectra here. So I opened this image here in the RSpec software. This is the software which came with my grating, right? And so this is the image I put, which I have showed you. So it will show me this zeroth order, and then is curve like this, where I have some absorption lines, and it is easy to calibrate. Right now, it is showing me the pixel numbers. Okay, these are the pixel numbers. Fine. And in order to, I'm showing you only one little thing. You want to calibrate. So if we calibrate this, you have to put it this zero here and then the pixel. What is general lines would be there, absorption lines. The hydrogen beta is generally on the left side of the peak. Okay, so if I select this, then as you can see now the pixel numbers have changed to angstroms here, right? And the first we can compare it with the elements. The software comes with a whole set of libraries of standard lines, wavelengths of lines. And if I click it here, hydrogen bomber, okay, so this is H beta, this is H gamma, and H alpha is not prominent because of the reason that I'm using a DSLR camera used for civilian use at daytime, and I'm using it for astrophotography. So it has a filter to block the IR and so lines, and that's why it's not so good. But if you are using an astrophotography camera for such a thing, then we'll get a good dip showing us H alpha, beta, gamma, and so on. And then this can be calibrated to find the type of stars. Let me open the reference library because this is this corresponds to Vega. I had taken the photograph of Vega, and it is A0 with kind of pi kind of star, and see this H beta very corresponds. Similarly, this also is at the proper position. Fine. So this way, and there are other steps also which cannot be covered, of course, in this lecture. But this can be calibrated to find the type of stars, the temperature range of stars, and the wavelengths. Of course, other small calculations, redshift, and other calculations can be done. So if you have a camera and you buy a proper filter, then let me skip all this. See? This is what I showed. This okay, and this is the final calibrated spectra, the red one, compared with the library spectra which is supplied by the in the software. So that can be done. I think I have many more things, but we are nearing our 50 minutes. So, should we have a question answer session, or
You can
you
continue
can
for a
continue
few
for a few
more minutes, sir.
more minutes, sir? Okay, fine. I will try to quickly cover this. See, this is not about photograph. This is about constructing an eclipse diagram. Suppose there is a lunar eclipse, and you want to know what will be the progress of the eclipse, when it will be the first contact, and how much it will be covered, and so and so. Then we generally go to the NASA eclipse page, everybody, and this kind of graphical display is given where this is the Earth's penumbra, this is Earth umbra, this dotted line is shows the ecliptic, and there are various times, say P1, U1, and so on. When it touches the first contact with the penumbra, first contact with umbra, and so on. So here also we need to draw proper scaled sizes of the penumbra, umbra, and the progress of the eclipse. I mean how the moon moves with respect to time. And for that, we need to find the local time of the full moon. From a good ephemeris program, we should find the longitude, latitude of the moon, and time of the 1 hour before and 1 hour after the full moon, the parallax, etc. So if you have a good ephemeris or planetarium program and you get hold of this data, then these things can be calculated. This is the three different hours. Actually, full moon is at 23:40, but 1 hour before and 1 hour after, I have computed all this. Okay, so the difference of these two divided by 2 will give you the hourly motion of the longitude of moon, that is delta lambda. Similarly, the difference in latitude, the rate at which the latitude changes, longitude of the sun, so the rate of hourly motion of the sun, and parallax, this is the size of the umbra, the size of the penumbra, and this is the size of the umbra. This is radius. So once you get hold of this, and this is very easy, you can open a good ephemeris planetarium program and you can have access to all this data. So you just have to prepare this table and calculate this first. Then we need to convert it into centimeters. See, actually the size of the penumbra is in degrees. This is size of the umbra in degrees. Okay, this is also in degrees, but we need to plot it on the graph paper to get an idea. So it has to be converted to centimeters. And another thing, with time, the position of the moon changes. So this is what we have to do. Simply find the difference of the rate of change of longitude of the moon and the sun, and this is this many degrees per hour. Okay, and then you have to simply convert it into centimeter. So once you do this, first draw the ecliptic. Here you select a time axis, and I selected a scale 1 hour is equal to 2 centimeters. So this is 8 p.m., 9 p.m., and so on. If you have the we already computed the beta, the no latitude of moon. So for any given time, if you just need 2 points. Actually, it's a curve, strictly speaking. But if you are creating a diagram like this, then latitude of moon at one point and another point, draw a straight line, you have this line. So we can see here that the moon path is going from below the ecliptic at early morning and going above. So this is the ascending road. We simply put umbra, penumbra. We have the radius in centimeter. Then we take the radius of the moon in a compass and then move the metallic needle here and see where the pencil first touches this. And when it is at this point and it touches first time, we draw it circle like this. So this is representing moon with the first contact on penumbra, and then so on. Right? So this is not just a schematic diagram, this is a scaled down diagram which you exactly see on the similar you see on the web page. The difference is that there the ecliptic was slanting and here I put it like this. Similarly, we can do it for the solar eclipse also. So these are, but these are workshop activities which we are more adapted for offline. I think I've completed my time. So let me finish this. I have many more things, but maybe some later time. So we can, if there are some questions, we can interact.
Thank you so much, sir, for such an interesting talk. And I never knew so much quantitative measurements and physics is hidden in the observational astronomy. I learned so many things about the measurements, and I think 50 minutes are not enough for such a big topic.
For solar eclipse and other things, we need a offline would be better, where I can instruct, go and see what the people are drawing.
Yeah,
but as far as size, phase, etc. is concerned, this is fine.
You are right, sir. We can have another offline workshop also for such kind of learnings.
Sure.
So
sure, I will help.
Thank you so much, sir. Now the floor is open for the question and queries. Yes, any question? We have with us Dr. Kulkarni also, Dr. Arvind Kulkarni. Yes, sir. Sir, my question was that what was this CAD CAD program? Is it available free source? Can we download it?
Yes. Yes. The CAD program which I am using.
Can we use it on Windows, sir?
Yes, it is my PC is my laptop is window based, and the name is Libricate.
Okay.
This
And
one.
what about, sir,
Yes.
RSpec software?
RSpec software comes with the grating, and
Okay.
that grating because it is 100 lines per mm, and one thing is it is made in a circular form factor, so that it can be plugged before your lens, camera lens.
Okay.
It goes with an adapter, and it is a paid version. But there are other softwares which you do a photograph, I mean a spectra of a star, and there are other softwares which are freeware, like VSpec is there instead of RSpec. It is VSpec, and then there are other two or three other very good softwares. They are freeware. They can be used. But
Okay.
because I purchased it that grating, I purchased the software also. But others can be used.
And son, about the measurement of phase, it is the measurement along one month or 1 year.
No, phase any given time, because
Okay.
phase will be different no daily. आज छठ है कल सातम like that. So
Perigee and
you take the
apogee
picture. Oh, that is for finding the orbital eccentricity.
eccentricity. Yes, it is
Right.
for it is 1 month.
Eccentricity, separated by 27.50. So one picture at perigee
Okay.
day, another at apogee day, right? And then we have to plug in those numbers.
Right, sir. Thank you. Any other question?
Good
Doc-
evening, sir. Mayur here.
Mayur, good evening.
सर एक क्वेश्चन है रिगार्डिंग दी प्लैनेट फोटोग्राफी.
Yeah.
मतलब ये हमारा जो एटमॉस्फेयर होता है उसकी वजह से जो मतलब एंगुलर डायमीटर होता है उसमें कोई डिफरेंट पिक्चर और एटमॉस्फेरिक की वजह से जो पिक्चर में डिस्टॉर्शन आता है वो हम कैलकुलेट कर सकते हैं.
Turbulence, because of the atmosphere is turbulent, right? Transparency is not good. Then you will get a kind of if it's a video, it will be wobbling. But if you are taking a picture, then it will show you, kind of defocused. So when that is the case, you should take a video, extract the frames, and then stack the best frames out of those. Then you will get a good picture. Otherwise, if the transparency is no turbulence, even a single shot will be fine.
Okay, sir.
Dr. Kulkarni, sir. Okay. Dr.
I think there are no
P.K. Aluwali, sir. Kindly you give us your comment, sir. Hello, P.K. Aluwali, sir. Are you there?
I think his microphone.
Hello,
Mute.
am I
Yes, sir.
audible?
Yes, sir. You are audible, sir.
Yes.
So thank you very much, Professor Brijmohan, and it was an excellent tutorial. I think I really enjoyed it. I must compliment you for excellent graph work. I think that was a treat to watch. People are forgetting that art now.
I first do hand calculations, then calculators, then I move to computer if needed. I have a various calculators, a programmable calculator is also there, but I always prefer hand-drawn graphs compared to computer-generated graphs. Thank you, sir.
I think it was just great and so engaging. I think one full day can be utilized for doing this whole exercise. But
Right, sir.
there was so much to learn and so much to reveal for the mind. I think that was just excellent. In fact, sir, let me tell you that today was the 40th talk of our National Astronomy Network of IAPT. And we have in fact created and curated 40 very good videos which can be, properly classified to provide an introductory course on astronomy itself. I think that's the best part which has happened as a result of this network itself.
That's a very good initiative. So we have to try for more number of people joining so that it spreads even more.
And in fact, this time I was telling Himanji that IABT is not very rich, but still small amount can be given for holding offline workshop also somewhere.
Right.
One day if we can spend and if we can provide, say, good dinner and lunch to the students that day, it will be worth it. And
This kind of
something can happen simultaneously at different places in the country. Simultaneous workshops can be done because I think when you planned all these things, I was able to see the kind of planning one needs to do in terms of where the moon will be after so many days, where it will be. And this LibreCAD also, is a wonderful software.
Yes, it's a freeware, so no tension. You don't need to purchase. And this kind of workshops I do for my MSc students. Those who are interested in astronomy, I just make them plot the lunar eclipse, forthcoming lunar eclipse, or recent past का अगर कोई solar eclipse है, तो I just teach them how it can be, scaled diagram can be done so that they know beforehand that at my place the eclipse will appear like this at this particular time. Of course, all websites do contain, NASA and other websites have all those graphics, but to be able to do it ourselves, that gives the real joy.
This is the confidence also which one gets. So these are the things which one can do with hand. Right. And it's just great. I have no words to express my sincere thanks to you on behalf of IEPT. It is just wonderful. I normally don't miss NASNI talks. I enjoy those. And I'm like a novice sitting here trying to understand what is going on. Just great. You gave wonderful possibilities where the data is sitting, from where you can access the data. So this talk is worth seeing again and making notes particularly. Normally, I always tell people that when you are listening to a talk and if you want to engage yourself, you must keep a notebook with you and try to make your notes. Because that is the best way to carry the impression with you later. And you can always read. The best part of these YouTube videos is that you can always revisit
it can be replayed, right?
So once again, thank you very much, and thank you, Hemant. You are doing just a wonderful job, and congratulations to the dedicated group of NASNI for achieving this mark of 40. So very soon we are going to have our golden week also, when we will have the 50th talk.
Yes, sir.
So we will celebrate it.
Thank you. Thank you so much, sir, for your blessings and inspirations. Any other question, Madam Deka? You want to say few words?
I would also like to thank Professor Brijmohan. It was really a very wonderful talk, and I also really enjoyed how the supermoon can be seen. And I would also like to know if the blue moon or the red moon, they all happen during that supermoon time only.
No, supermoon is when the full moon is, extra large, relatively extra large because it is nearer. Blue moon, the word blue moon is used for, the second full moon of a month. So in a calendar month, if you have two full moons, and that happens because if you have a full moon on, say, the first of a month, the full moon to full moon period is 29.53 days, the synodic month. So if there is a full moon today, after 29.53 days, there will again be a full moon. So that way, if on the first or the second, we'll have another full moon in the same calendar month, and that is when we say once in a blue moon. But under special conditions, the moon can appear having a bluish or greenish tint, and that's because when we have particles, say from a there is a volcanic eruption or something, and we have a fine ash in the sky. and the moonlight is coming from within these ash particles. Because of the particular size of the particles, certain wavelengths will be scattered and others will not be scattered. So at that time, bluish or greenish tint may be visible. But otherwise, blue moon means second full moon of the, nothing to do with color.
But will it occur at the same place where the supermoon was there, or on the other side?
Pardon? Did not understand.
Will it occur at the same place? I mean, same position after a month, or
No.
will be in the other side?
Whenever it is full moon and it is above the sky in the night time, it will be visible. And moon is quite near. So it's not like one place or the other. Wherever there is night time and it is full moon, it will be visible from all the places. So lunar eclipse is visible from, kind of half the globe. But if it's a solar eclipse, then place is important, right? Because it can be total at some place, it will be partial at some other place.
And as President Sir said, I also enjoyed your graphical drawings very much. I really enjoyed. Yes.
Thank you, madam.
Thank you so much. Thank you so much for this wonderful talk.
Thank you so much, madam. And it was really an interactive and very interesting talk, giving the glimpse of all kind of measurements we can do. And I think these measurements are very important for, I think, undergraduate students who want to take some projects along with their major subject, and very practical and worth learning topic of measurements. On behalf of NASNI and IAPT, I want to extend thanks to Dr. Brijmohan Thakur for sparing time. I know you are always busy in your university and your classroom work.
For astronomy, I am not busy.
But I was willing your talk in the starting of this year, but we extended because you could not find time. But this time we are privileged that we get your time for this talk. And from all the members and from NASNI, once again, thank you very much, sir. And I wish we will get one more talk from your side on such kind of topic. And I want to thank our members, senior members, Professor P.K. Aluwalia sir, who is always with us in this during this talk and inspire us with his presence. And Madam Deka is always there. She never missed this talk, and in all the 40 talks she was with us. Thank you very much, madam, for encouraging me as well as all other members. Thank you very much, and I extend thanks to all the members who attended talk today. So thank you very much. Now we close this session to meet in the next Wednesday talk. Thank you all. Thank you very much. And